So let's have a look at some real simple molecules, an example of how all this works out. And we're going to take methane as the example. Methane is the most important component in natural gas. It's also a greenhouse gas. Methane has one carbon atom which is surrounded by 4 hydrogens. The molecular formula is CH4, so there are 4 carbon-hydrogen bonds in the Lewis structure. And because there are 4 carbon-hydrogen bonds, that means the central carbon atom of methane is surrounded by so-called 4 electron domains. And domain is a part of space where electrons are. In the case of methane, these electrons are in the 4 carbon-hydrogen bonds. And so these 4 domains or electrons, they avoid each other as much as possible due to electron repulsion. And as a result of that, they occupy an area of space, the various electrons in the bonds occupy an area of space to be far apart from each other as they can possibly get. So let's have a look at this for the case of methane. And so we have 1 electron domain in this carbon-hydrogen bond, 1 electron domain in this carbon-hydrogen bond, and 1 in this one, and 1 in this one. These are our 4 electron domains. And the geometry that they will acquire in order to keep as far apart from each other as they possibly can get is a so-called tetrahedral. What that means is those 4 electron domains will fit within a tetrahedron, 4-sided 3-dimensional figure as shown here. And so the electron domain geometry where the electrons are in methane they have a tetrahedral geometry. They fill a tetrahedron. Each of these electron domains are associated with another atom, a hydrogen atom, the central carbon atom, and so on. And remember, we decided that it's the positions of the atoms in the molecule that determine the molecular geometry. The geometry of the molecule is determined by the positions of the atoms. Because we have 4 atoms at the end of these 3 electron domains, we have 4 bonds, we have 4 additional atoms, and because of the electron domain geometry is tetrahedral, then the positions of these atoms are also tetrahedral. And so the molecular geometry is also tetrahedral. So in this case, the electron domain geometry and the molecular geometry, 2 different things, they turn out to be the same because each electron domain is associated with the position of another atom. So let's make sure we understand what that tetrahedral geometry means in 3D space. Again, let's look at a molecular model to do that. So here we have a computer model of methane with the central carbon atom and the 4 hydrogens. And if we rotate the molecule, we can clearly see this tetrahedral geometry. So tetrahedral is the geometry of the molecule. It's also the geometry of the 4 electron domains, right? 1, 2, 3, 4. So in this particular case, the positions of the electrons in space, the important electrons in space, correspond to have corresponding locations for atoms in space. So the molecular geometry and the electron domain geometry are the same in this case. So methane has a tetrahedral molecular geometry, and all the carbon-hydrogen bonds are the same length, and all of the bond angles are the same also, roughly 109 degrees. And you notice that the angles are not 90 degrees, and they're not 90 degrees because that's what VSEPR tells us the bond angles have to be with the electrons avoiding each other. If we look at another example, ammonia. Ammonia has a molecular formula NH3. It has a central nitrogen atom surrounded by 3 hydrogen atoms. It follows the normal rules of valence. And just like methane, the central nitrogen of ammonia also surrounded by 4 electron domains. So we have 1 domain in a nitrogen-hydrogen bond. In fact, we have 2 other nitrogen-hydrogen bonds. And this time, the 4th electron domain is this non-bonding pair of electrons on the nitrogen. So again, we still have 4 electron domains, which means the electron domain geometry is tetrahedral, just like it was in methane for exactly the same reason. But in this case, only 3 of the electron domains are now associated with other atoms on the molecule. And remember, it's the positions of the atoms in the molecule that determine the molecular geometry, the geometry of the overall molecule. And so in this case, we can only identify the positions of the nitrogen and the 3 hydrogens, and those atoms are not going to define a tetrahedron in this case. They're going to define a triangular pyramid. So in this case, we have 3 bonds to atoms. And so the molecular geometry can only be defined by the positions of the atoms, and this is a trigonal pyramid, or the geometry is trigonal pyramidal. So because of the non-bonding electrons, the non-bonding electrons will define where the electrons are in space, but they don't define the geometry of their overall molecule. Let's have a look at trigonal pyramidal geometry again on the computer to make sure we understand what that means. So here is a molecular model of ammonia, the nitrogen and the 3 hydrogens, and we can see the molecular geometry is certainly not flat planar. It has this trigonal pyramidal geometry, where the trigonal pyramidal refers to the fact that it fits inside a pyramid with 3 faces, a triangular pyramid if you like. And again, so the molecular geometry in this case is different from the electron domain geometry, because the molecular geometry is defined only by the positions of the atoms, whereas the electron domain geometry is also defined by the positions of all the electrons around the central atom. So in this case, the molecular geometry is trigonal pyramidal. So ammonia has the trigonal pyramidal geometry. However, if we look at the bond angles still turn out to be almost exactly 109 degrees. In ammonia, they're actually close at 107, but we're going to assume that 109 degrees that's the bond angle whenever we have a tetrahedral electron domain geometry as we have here. Let's look at another example. A classic example is water. Most of you will probably know that water has this bent structure. We're about to find out why. Water is obviously oxygen with 2 hydrogens attached, and if we look at the central oxygen of water, again we find there are 4 electron domains. There's one domain in one oxygen-hydrogen bond, another domain in the other oxygen-hydrogen bond, and then in this case there are 2 non-bonding pairs of electrons. So again, 4 electron domains. This means that the electron domain geometry is again tetrahedral. The 4 electron domains avoid each other as much as they possibly can. But in this case, oxygen only has 3 atoms. And remember, it's the positions of the atoms only that determine the molecular geometry. And so in this case, the molecular geometry of water can only be defined as bent. So it is bent because we only have 2 other atoms. But again, the bond angle, the hydrogen-oxygen-hydrogen bond angle, the HOH bond angle, again is roughly 109 degrees. In water, it's actually a little bit closer to 105. But again, for all molecules or all atoms where we have tetrahedral electron domain geometry, we're going to assume a bond angle of 109 degrees. And of course, this is the reason why water has this classical bent structure. Again, let's just have a look at that on the computer model one more time. So here is a single molecule of water, oxygen, 2 hydrogens. Again, it has this classic bent structure. The 2 pairs of non-bonding electrons are not included because the model only shows where the atoms are, not the electrons. But there's 1 pair of non-bonding electrons roughly here and 1 down here. And this is water with the classical bent structure. So the geometry around a particular atom is determined by the positions of the other atoms around that atom, and those are determined by the geometries of the electrons around the atom, and VSEPR tells us that those arrange themselves in space to minimize their energy. We get all that by now. In this case, all the examples that we looked at so far, the molecular geometry is actually the geometry of the entire molecule. Most large molecules we won't be able to define that way, so in the next video we'll talk about how we handle situations where we have quite a large molecule, and then we're asking about the geometry within one particular atom within that molecule.